Okay. How are you, Arthur? Okay, now the sound is on.
Could you introduce the speaker again?
Hi, we are very fortunate to have Yury Polyanskiy, me, as the next speaker. Yeah, so I just said that this is a joint work with many people over the years, and I'm from engineering and computer science department, so I don't belong to either physicists or mathematicians, but I work on information theory, which is, I guess, relevant to both. Okay, so let me start by just mentioning two things which are important for my talk. So, okay, in information theory, our objects are random variables. Okay, or I guess more rigorously, I should say they're measurable spaces. Okay, and the arrows, which I will draw between the objects, are noisy channels. And I will explain in a second what I mean exactly. And again, for mathematicians, noisy channel is the same as the Markov kernel. Okay. Okay. So an example of a noisy channel would be this arrow X, Y, which I will call binary symmetric channel with parameter delta, BSC sub delta. Okay, so this is a channel which takes a binary digit, produces another binary digit according to the following rule. So if the input is 0, then the output is 0 with probability 1 minus delta, and with probability delta, it gets flipped to 1, and the symmetric picture for the input 1. Right? So this is what the arrow means, and whenever you see this arrow in my diagrams, just remember this little notation. Okay, and another piece of background is that, again, I hope most of the people seen this before, right? But when I write IXY for two random variables, right? So what I mean is the difference of entropies, right? This is just a classical Shannon mutual information. Okay, so with this initial setup, let me tell you about some very basic question in one dimension, just to set the stage. Okay, so what we will do is the following. So let's take some unbiased bit, right? Unbiased coin flip, x0, right? And let's pass it over binary symmetric channel, right? And let's suppose it enters some kind of relay station, right, which can do something on this bit, and then, you know, the output of this relay, of this computer, right, which looks at the bit, and right, so it passes for another, and so on, right? And let's say that the output of each channel, we can call it y0, right? The input of the next channel is going to be, you know, x1, and so on, right? And so this continues for n hops, right? And we get a diagram like this, right? Notice that each function here, fj, right, each relay function is a function from binary to binary, right? So there are very few such functions, right? So, okay, so the question that we want to ask, right? So question, what happens to mutual information between the first and the end, right? Okay, so notice, so let me first give you what I call probability theory proof, right? So probability theory proof would be the following. So you would say, okay, let's consider a special case when all fj's are identities, right? Okay, so then you can quickly see, if you had more time, right, you would very quickly, or maybe you can see it on the fly, right, that when you just concatenate all these channels, right, the resulting transformation is just BSC with some parameter tau, right? Where tau, I mean, this is a convolution on Z2, so you can compute, right, that tau gets, you can just compute the expression for tau from this equation, right? And this means that tau is 1/2 minus 1 minus 2 delta to the n over 2, right? So the important piece here is that tau converges to 1/2, right, exponentially fast, right? And this implies that the mutual information between the input and the output, right, is e to some constant depending on delta, right, scaling as right, decaying exponentially fast, right? So this is a quick demonstration that, okay, if your job is to push the bit through a sequence of noisy channels, if you just apply the identity transformation, right, then this is not possible to, right, so the bit will decay very quickly. Now, the bad part about this proof is that this only works for identity, right? What if you apply some other functions? Well, there are not too many interesting functions here, right? So, I mean, the other interesting function could be not, right? The inverse, right? But then in this case, I mean, the only thing that would change, right, is that you would still get this, and then depending on the sign, you would still get tau, which is 1/2 plus minus, right? Because nothing changes here. So, and still this derivation is correct, right? And of course, the other functions are what? I mean, f is constant 0. This just terminates transmission of information immediately, right? So that's it, right? So we can see that nothing interesting is happening here. Okay, so let me just say that again. So this is a probability proof which I did by enumeration, right, of possibilities, right? So there is a slightly different proof, right? Let me show you different proof, right, which is more generalizable. Okay, so there is a concept of data processing. Okay, so suppose you have a chain like this for a bunch of random variables, and the last arrow is the BSC channel, right? So then there is this thing called data processing inequality, right, which tells us that mutual information between A and C cannot increase, right? So the mutual information after you pass through a channel, right, should necessarily decrease, right? So this is the standard thing that everybody uses all the time. Now, a slightly less standard thing is so-called strong data processing inequality, which actually says that when this last link is a BSC channel, then not only mutual information decays, it actually decays by 1 minus 2 delta squared, right? So that's a precise statement, right? And this is very, I mean, this is fascinating fact, right? Because I really love this fact. Like, I guess in the last, I don't know, 6-7 years that I work on this and related questions, I just can't sort of get enough of the beauty of this identity, right? Because it says that, right, so that there is a very concrete way in which noise destroys information, right, multiplicatively, right? Okay, so, but in any case, so in our language, right, we can apply this and get that, well, inductively, right, if we apply, right, so we can get that ix0 yn is upper bounded by 1 minus 2 delta squared ix0 yn minus 1, right, and so on all the way, right, to log 2, right? So we can just apply this identity many times, right, through the chain. Okay, and we get this explicit exponent here, right? This is a slight benefit, but that's not the main benefit. The main benefit is this proof generalizes, right? So this proof generalizes to other channels. Notice that here I never asked what is the FJs, right? So this is the beauty of this proof, right? So this somehow doesn't require enumeration of the possibilities, right? So in particular, for example, for the Gaussian channel, for additive Gaussian noise channel, I mean, the situation is a little bit more murky, but you can show that ixyn also goes to 0, but only as log n over log n. Okay, so, and notice that for Gaussian noise channel, right, I mean, the relays are functions from real to real, right, measurable functions from real to real, right? So that's why it's a little, right, so enumeration is not possible, right? So that's why, so I will show you some other results, right, for which we have probability type proof, but we don't have IT. This is what I call information theoretic proof, right? Because it's somehow, I don't know, it uses information measures. So for the main result that I wanted to show today, we don't have IT proof, and I view this as a disadvantage. Okay, so let me, yes, that's right. I can just lift this side as well, right? Okay. Yeah, okay, so, right, so let me go to the 2D case. Right, okay, so the 2D case. Okay, so right. So what happens if you try to do this information propagation in 2 dimensions? Okay, so I need to draw this carefully. Okay, so we start with a bit which now has x00, right? Again, this is unbiased bit, right? So it gets sent in 4 different directions in the beginning, right? Because we are in the middle of the 2-dimensional square lattice, right? Okay, so now here it encounters some processors, right? Again, so all arrows are BSCs, right? So when the bit traverses through this arrow, it can get flipped with probability delta, right? Right, and so we get a picture like this, and so on, right? And I mean, symmetric picture in other quadrants, right? Okay, so notice that something interesting is happening here, because in 1 dimension, right, we couldn't, basically the information gets destroyed but never added back, right? But here, this intermediate guy, right, it has 2 inputs, right? So possibly he can try to clean up information a little bit, right? And you know, potentially remove some of the deleterious effects of noise by doing that, right? So, okay, so what is the question here? So the main question is whether we can come up with a smart processing functions. Let me give names to these variables. The output of this processing function is going to be x01, right? This is x11. This is x02, right? And this is going to be x20, right? So we can ask the following question: whether the mutual information between x00 and a set of all outputs at distance n, right? Does this go to 0 or not, right? As n goes to infinity. Okay, so this is the main question, right? And the conjecture is that yes, regardless of how you pick these functions, in 2 dimensions, you cannot propagate information to the infinite boundary, right? Again, so the picture here is that this is our origin, right? And in my mind, what happens is we start this information wave, right? And what I'm asking is whether the information wave dies, right? So does it die regardless of how you do it or not? Okay, so let me show you a calculation which kind of suggests that indeed this is going to be true. Okay, so let's do first attempt. Okay, so notice that there are 4 times 2 to the n paths from x0, from the origin, right, to the n boundary. Right? So you first choose where you go, northeast, southwest, right? And then you only decide up or down, right? Or sorry, up or left, right? So there are this many paths, right? So I don't know if you guys can see this. Let me just slide it up, right? Okay, so right, so then you can apply, you know, this estimate that I showed you, the strong data processing inequality, to show that, you know, what you get here is something like this, right? Because you're just counting overall paths, right? And along each path, you encounter n different BSC channels. So each one contracts by 1 minus 2 delta squared. So this is the contraction, right? Okay, so why is this cool? Because, well, you can immediately see that right, so you can immediately see that, right, so this mutual information, the information wave dies out if 1 minus 2 delta squared is less than 1/2, right? And you can use some of the ideas from our paper from 2017 with Yihong Wu. You can improve this analysis a little bit. So instead of comparing to 1/2, you can compare it to PC, which is the threshold for oriented bond percolation, or oriented bond percolation. Bond percolation on Z2. Okay, so it's not trivial, right? Because it's not like the links are, so there is some theorem there, right? So the result that indeed overcounting the paths, right? You can reduce this by comparing to, okay, but in any case, this only works for deltas which are very close to 1/2, right? Or close to 1/2, right? So this does not, right? So the main question, right? Remaining annoying question, what about delta going to 0, right? If the noise is very, very low, right, then information will propagate for a while, right? The question is it actually going to be destroyed by some deltas which are very low? Okay, so this we resolved in 2 joint papers over a few years, joined with many people, Anurag Makur, Elkanan Mossel, who is actually here and is going to give another talk on Wednesday, also Chenghao Guo and Guy Bressler. Okay, so there are 2 different papers. So with them, we resolved this, right? So we proved the following result, theorem. If all Fj's, if all Fv are the same, if all the processing functions are the same, then there exists some delta 0, well, right, such that for all delta less than delta 0, the information wave dies out. Okay, so that's the main result. Let me check how I'm doing on time. Yeah, I think I should be able to show you. The cool part about this result is that in the spirit of the previous talk, there are 2 different parts there, right? So one is probability part, which I will just sweep under the rug, and the other part is something that I was a little bit hesitant to present here because it's computer-aided proof, right? I thought you guys are going to say, come on, there's no proof, get out of here, right? But I noticed that many people in this room, right, so far, I mean, and yesterday and today, right, use computers so I hope that's okay. In any case, so let me, right. Okay, so how did we show this? Here's an idea. Okay, first we use something known as coupling. So technique from probability theory or Markov chains, more exactly, known as coupling. Coupling, okay, reduces the question to the study, the question to analysis of some strange Markov chain, Markov process, okay, which acts from 0, 1 question mark. So it's a Markov process on the ternary alphabet. Okay, so it acts from n to n plus 1. So there's explicit kernel, right? So it's explicit probabilistic kernel, which actually has a fairly nice description. So it like takes this n values, right, n spins, and produces n plus 1 spins here. Again, they're ternary spins, right? Okay. So, right, so once you reduce to this Markov process, what you need to show, right, for this process, we need to show that it kills all question marks in finite time. Okay, so basically there's some kind of evolution on this kind of growing structure, right? And then what we need to show is that the number of question marks gradually decreases over time, right? So to do that, right, so we can show that this indeed, I mean, this Markov chain is parameterized by the crossover probability delta, right? So what we showed in the first paper is that for every delta, this is true, right? So for every delta, star is true if a certain linear program is feasible. Okay, so this is what I wanted to finish with this piece, right? So okay, so in the first paper, right, we were able to show that, okay, give me any processing function, I can construct this giant linear program. If it's feasible, then there exists Lyapunov function, which shows this Markov process contracts and kills all the question marks. And then this in particular shows that mutual information decays by the coupling argument. Okay, so this was cool, but notice a small subtlety here. So we can check that for every delta, oh, these are polynomial, by the way. So poly in delta, right? So the matrix and the column vector, right, which are, okay, so we can check it for every delta, but what we need to conclude, right, that there exists some delta zero, we need to check feasibility in the interval, right? So no matter how many deltas we check, we can't conclude that that it works for some continuum of them, right? So we decided to ask this question: how can we analyze feasibility in the local neighborhood of a linear program? Oh, wow, this is high friction. Oh, there's a board behind. Okay, yeah, I'll just right. So yeah, so we define, right, so we made this definition that you know, the A of delta X is locally feasible. This linear program is locally feasible, we call it LF, if there exists neighborhood of zero, neighborhood U of zero, such that, well, for all delta in the neighborhood, right, I mean, the LP is feasible. It's feasible, right? Exists a solution. Okay. Okay, so, right, so, and then, okay, so here's, oh yeah, let this be a vector actually, right? So let delta be a vector, so it can have multiple entries. So here's the fun theorem from the second paper, which I also wanted to show here. So if delta has only one parameter, which is our case, then there is a cool polytime algorithm. There is a polytime algo. I'll go for checking LF, okay? And if delta has more than one parameter, delta D bigger or 2, then it's NP hard to do local feasibility, to check local feasibility. So that's another sort of fun example here that, you know, going one dimension up somehow makes things much harder. In any case, so once we had this, right, we could apply for every different processing function, which are not too many again, right? We could construct this linear program and show its local feasibility using our algorithm, right? So our computer-aided algorithm actually provides a certificate in rational numbers, right? So you can plug in and certify that indeed every different processing function kills information here. Okay, so I think I'm close to, oh yeah, I still have some time to talk about 3D case. Okay, so before I go to the 3D case, I wanted to say what is bad about our proof. So what are some other open things in 2 dimensions? Right, okay, so open in 2D. Okay, so the first thing, which is the most annoying thing, right, is extend from fixed FV, right, to general case. And doing that will require finding an information theoretic proof. Remember, my first proof with counting the number of paths, right, was very elegant. It didn't require any specifics about this, you know, functions. And here the functions enter like crazy, right? This linear program, which is like, you know, tens of thousands of dimensions. I mean, this function enters every entry in this matrix in a crazy way, right? So, okay, so this is what I call IT style proof. So I don't have it. And this annoys me a lot. Okay, so this is the first problem. The second interesting issue here is that even if you don't care about extending to, you know, this fabric which is space non-homogeneous, right? Which again, for physicists might not be as interesting, right? Let's suppose you are fine with space homogeneous fabrics, right? Okay, so well then still there is a gap, right? Because we proved that for delta less than delta zero, the information wave dies out, right? And for delta bigger than this delta percolation, right, it also dies. But there is still a gap here, right? What about delta between delta zero and delta percolation? In principle, you can close it by running our LP. You know, you found one interval, then you move a little bit, you find another, right? And you just cover the interval. But it's just computationally impossible because our delta zero is very small. So we can't rerun it so many times. So again, so this is and I think the third and more constructive question is, we can construct other lattices, other two-dimensional lattices, for example, not nearest neighbor, but like two neighbors, right? Two nearest neighbors, right? Where you're allowed to propagate information across two neighbors, right? So other lattices, right? Can you pass information, dies or not? Okay, so this is some open stuff in that direction, and let me mention a few things about three-dimensional case. So three-dimensional case, I don't have any rigorous statement, but I wanted to show you some connection to a famous Thom's automata. So 3D. Okay, so let's look at the 3D case. So we start our bit from here. I'm trying to draw a cube here, right? So, okay, so this is my initial bit, right? And at the first time instance, it gets sent to these three vertices, right? So nothing interesting at first time step, right? The second time step, it gets, right? So the bit gets propagated to here, here, and here, right? And again, so far, nothing interesting is happening. But at time 3, t equals 3, what will happen is that we will get to this vertex, right? And this vertex has 3 inputs, right? So in 3 dimensions, most of the vertices have 3 inputs. Okay, and now for 3 inputs, right? There is a very nice function, very nice Boolean function, right? Of 3 inputs, which is what? Can anybody suggest? Majority, right? Of course, indeed, right? So here, right, if you take FV to be the majority, right, of the 3 inputs, it's beautiful because notice what happens for majority. If suppose you start with some very low noise, right? So initially the information propagates and propagates, just so you start with 0 and it's just all wave of zeros, right? Then occasionally one of the links will introduce an error, right? But then the majority will squish that error, right, and kill it and clean it up, right? So the majority, and I mean, if you know like the story of fault-tolerant computing, how von Neumann, right, played with majority. I mean, this story sort of goes, you know, appears all over, you know, in the cellular automata and mathematics, right, all the time. That majority somehow has the property of cleaning up noise, and indeed, so Andre Thom in 1980 showed that majority. So majority in 2D, majority vote in 2D, something known as NAC rule. He showed that it actually, right? So if you think of it as a noisy cellular automata, so this majority, right? So you think of the operation on the infinite. On the infinite square lattice, right? So if you first apply this BSC noise and then apply majority, right? So then Thom showed, this is a major achievement, right? That this cellular automata actually retains information indefinitely, right? So it doesn't, and this suggests, right? So for a while, I was always like hoping that we can easily show that this implies, right? Because you can look at evolution on the slices here, and this is like a local majority with 3 neighbors, exactly Thom's rule. So it suggests that there should be, you know, information wave propagating in 3 dimensions, which is a beautiful situation, right? In 2D, information dies. In 3D, it actually expands indefinitely. But now I'm not so sure because, you know, if you look at the planes, like at the cut planes here, right? On them, the evolution is 2-dimensional, and we know that it couples in finite time, right? So this means eventually, right, on the boundaries, you will couple, so you forget information, right? And then the coupling will start to, you know, slowly, potentially, right? It can slowly sort of spread its tentacles inside the bulk. So it's not clear. Now it's 50-50. I wouldn't make a conjecture that I don't know if in 3D you can or cannot. Yeah, but anyway, so that's it. I'm roughly on time. Thanks a lot for your attention.
Again, questions with for microphone and.
Yeah, Marius Junge. So I was actually looking at your open problem number 3. Did you try something like free groups where you have 1 input, 3 output channels at every edge, at every vertex?
Okay, so
free groups are strange, right? But you know, it's you go in and you have.
Oh, I see. Isn't that a tree?
Yeah, it's a tree. Of course, it's a tree. Sorry.
So Elkanat Mossel here, that's right. So he's the mastermind behind a lot of this is called, that's right. So this is a very famous problem. If you draw a tree, then this is called broadcasting on trees. And there, actually, there's a completely beautiful picture, right? That, okay, so what happens on a tree is that at every stage, you copy information d times, right? And then it gets squished by 1 minus 2 delta squared. So actually, you can prove that information wave dies or doesn't die, even, right, depending precisely on the degree times 1 minus 2 delta squared.
Oh, wonderful.
Bigger or less than 1. So it's a completely beautiful characterization, right? And in some sense, there is nothing more you can ask, right? So if and only if it has a very explicit understanding, information copies and gets killed, right? But yeah, but we are nowhere near this.
Sure.
Yeah. And in the spirit of this conference, we should call it Bethe lattice, right? So on Bethe lattice, we're fine.
Oh, by the way, sorry, for the 3D picture, doesn't it depend on how you put your boundary at the end?
The boundary is still L1 ball, at least in my analysis, always, right? So it's always, yes, sorry, yeah. So.
Yeah, thanks for the very interesting talk. From the moment you said information wave, I just had a very physical picture in mind. So I was just curious to ask for, let's say, this third open question, how do you picture that actually happening? Because with a normal lattice, I can for sure picture like an interaction between nearest neighbors and nearest neighbors, but
yeah,
sorry, next nearest neighbors, but like a wave would kind of go through.
I think it's a beautiful question, but let me just say, I mean, I don't mean anything super fancy. I just meant, for example, this, right? So if you add diagonals, now suddenly you have 3 input gates here. Maybe that's already enough. Right, so we can try to run our LPs, right, on this. We didn't do it yet, but it's TBD. Right, does it answer your question?
Yeah, I suppose so.
Yeah, so right, so this was just, I mean, or you can also consider other, like, I don't know, hexagonal lattice, right? Compute them in some other way. I don't know. That's
and you don't think at all about the propagation in terms of interference or something like this?
Interference. Yeah, so you mean some kind of exogenous perturbations? So yeah, it's a good idea. I didn't think about this. Yeah, so you say like there's this probabilistic process, and also there's some random influence. Maybe you kill some edges randomly, right? Impurities, something like that. I didn't think about this. Yeah, but that's a cool question.
I think one more question.
Renato Renner, yes. I have a question about this matching or amazing formula, the strong data processing inequality. Yes. How far is there a generalization to some other channels? Because it seems to be a very peculiar thing for these binary symmetric channels. But for example, if you just had a lost channel or an not a completely symmetric channel, is there anything known?
Yes,
of
okay,
a similar kind?
It's a major topic of work in my group. Yes, so in general, this is hard to compute these coefficients explicitly. For binary input channels, there is a formula. Like it doesn't matter how asymmetric it is. But once you go beyond binary input channels, like for ternary input, okay, this used to be super hard, but last year we proved that for any channel, the SDPI constant is always achieved at a binary subchannel. So and for binary subchannel, we have a formula. So then if you have k inputs, it reduces to k choose 2 calculations.
Oh, very nice.
So in this sense, this is a characterization. Also, I want to say that the SDPI is always within multiplicative constant of the Hellinger square radius of the channel. So if it's
Okay.
Sorry, Neil and John,
So you have to go on, so that's not, we're gonna.
I'll talk to you. Yeah. Thank you.